All good. Hey, everybody. My name's Andy Reitano. I'm a technical evangelist here at Microsoft, and I'm here today to talk to you about some rules of thumb that I've picked up over years of working as a professional electrical engineer. It's only 30 minutes, 40 minutes, so I'm going to direct you to the slide so you can read it after. I'll touch on as many topics as I can, but I'm kind of here to just kind of give you some motivation if you're a purely developer to start playing with electronics. So I leave this picture in here to keep me humble. So no matter where I go in my career, I'm still moving equipment. So I mentioned I was a professional electrical engineer for 10 years in defense. Mostly did circuit design, high-speed PCB design, embedded C, some low-level stuff, and some FPGA development, which is kind of in between. And I'll cover that as we go along. I'm a ham radio, KD2DZM. If anyone else is anyone else a ham radio operator here? All right, sweet. I met him already. So interestingly enough, I joined on Microsoft last year, but before I joined, I founded a company called Bat Lab Electronics. We incorporated in New York, and we were mainly a PCB design house. So kind of a weird sweet spot between 100 and 1,000 of something is not something that's really feasible to do domestically. So we decided to, against all odds, start doing PCB manufacturing in New York. So initially, it was mostly to create flash cartridges or ways to put software on hardware so you can play it on like an old Commodore or Genesis or common gaming consoles. And what you see over here is kind of a flashing dock that was written and you connect over USB, and some Gerbers you send to the board house to be manufactured. And I was a BizSpark customer, which was very I don't think I could have done it without it. So before I joined Microsoft, they have a program called BizSpark that helps out startups that are just getting started. I think it's fewer than X number of employees, how much revenue you have, things like that. And basically, they're offering you full MSDN access, $150 credit, Azure credit, our portal, our cloud offering. And for 5 team members, so Windows keys, Office, anything. So if you are a startup, you should definitely talk to me after, and we'll get you on the program. I know I couldn't have done it without it. You know, our customer database, everything is hosted on Azure. And then I ended up working here through this connection, which is really excellent. So the biggest cart or hardware order we had was for a new game for the original NES, like the old console. And we made it hardware only. It's a 6502 microprocessor, which was really a popular one. It was in the Apple II, Commodore 64, BBC Micro, and that's 2K of RAM. And whenever I do these talks, everyone just kind of nods. And if I'm speaking to a younger crowd, I'm like, that's like 16 tweets. That's like no RAM at all. So we'd run this Kickstarter for this new game, and this was my old workbench, and it was fine, but it's not really a production spot, right? So, whoops, our Kickstarter was successful. And this is not bragging. This is just kind of like proof of point that, people want hardware. They want to hold things. And I'll cover some of that as we go on. But now we're 400% funded. Whoops. How do we manufacture that many PCBs in New York? We're in a weird area where I don't really want to send $40,000 worth of components from DigiKey to Shenzhen without establishing a relationship first. And I get to pay and train my friends, so now if I need quick turn, it's an investment to have somebody on call to be able to solder and assemble these boards. So here are like the first 100 that we had manufactured, and all of a sudden we're realizing we're getting a lot of data. We're having faults, we're having failed components, whatever it is. So we start collecting this data from and putting it out on our cloud, so we can start doing post-analysis and start predicting failures and things like that. So what this was for, the initial set was for a music album on an original NES cartridge by a band who they do their music and they play live, like a live rock band that has an NES on stage, and they wrote all the music and it's like playing the backing track. And you wouldn't believe how popular it was, right? So vinyl outsold digital downloads in the UK in 2015. And I think it's on an upward trend. And vinyl processing plants are backed up. And you go into a Barnes & Noble and it's like, Dark Side of the Moon, Pink Floyd remastered, and they're selling record players, and they're selling these things. And I think it's kind of it's kind of lashing back at the idea that you have everything at your fingertips digitally. You know, you have Netflix, you spend 3 hours looking for something, and then you watch it for an hour. And people kind of want to hold something again when they have Spotify and they could listen to anything and they can see anything. So I think like physical products are kind of like coming back. You know, there was you don't want to produce waste. You don't want to fill up landfills. But if you do it responsibly, I think people like owning stuff. Even in, a New York City apartment, like people collect records. It's like 3 milk crates and like a bed. And the NES Classic, even Nintendo couldn't predict its own demand. This thing was, I think they made 100,000 units. I don't have all the details, but this was just a snapshot when I originally put together this talk. And these were like, Forbes is like, you can't buy these things. And all it is like a little emulated Android-based box that looks like a Nintendo that plays old games. And I think it's like a rarity. I don't think they're making any more. And they sold out, and everyone's upset about it. But Nintendo could have made more and made more money. They didn't even know their own demand, right? So we started this manufacturing piece with, hey, let's just try it. Let's just do it in New York. We'll do our best. And it worked out really well. And there's a lot of reasons why it worked out well. And one of them is if you approach it from as a developer, if you approach a hardware project as a developer, you know how important it is to keep data or keep your systems functional. Just like you would create like a jig or something to help you with manufacturing, with software, you can solve a lot of problems with software. You can, have customer databases. You can have automatic dispensing of components and auto reorder or tell you when your stock is low. There are lots of like problems you can solve being a developer and bringing that approach to hardware. And I mean, it's it's not career suicide for me to say it, but because I work with software too, but electrical engineering, most of it is not that hard. So here's like the first technicians, and you can kind of see how it evolved where, that's like my old drummer and from my old band and like my old housemate, and they used to work for pizza and beer, but not anymore ever since we started making money. And this is them actually placing components onto the boards to be reflowed in an oven. Everything is surface mount. This is our first oven. It's a Black & Decker 4-slice toaster oven that had been modified into a circuit board reflow. And the reality is I bought one that was, I think it was $1,500 or something from a U.S. company that was somewhere between, proper manufacturing with a conveyor belt and everything. And this one outperforms it. It beats the pants off the one I bought for $1,500. What's really interesting about it is, and when it says, oh, there's no way you can place those parts so accurately, and the truth is we don't. We don't have a pick and place, but what an interesting byproduct of just having the correct amount of paste put on the pads is that once it becomes liquid, the surface tension is equal on all sides. So the parts will actually kind of like dance or shimmy into place. I don't know if I have a laser. I don't know if you can see my pointer, but you can see over here, this part actually moves like 50 mil. It's actually kind of dancing right into place. At the moment it becomes liquid and hits the right temperature to reflow, all the parts kind of self-align. And it's just because it's kind of sitting on a pool of liquid and it's equal on all sides, so it just goes whoosh, it clicks right into place. So now this is more what it looks like. I stopped torturing my technicians and brought them inside in like a nice heated spot. And it's been going great. I gotta say, so I don't have time to work on it anymore that I'm at Microsoft, but this has always been kind of a moonlighting gig. But it's kind of self-fulfilling in that if you set up the systems right, or you just dive in and try to solve the problem, and I'm hoping this is inspirational because I know there's some people here I've overheard talk about working on products, it might be fun just to try it. And I'm gonna show you why. So, by collecting this data from this oven, and we're constantly, we're using a Microsoft IoT Hub, which we set up on Azure, and it's sitting waiting to receive messages. We can do post-analysis on data. And one of the interesting ones was like, hey, one day all the boards, this one chip didn't reflow. The solder paste didn't flow correctly. And then we looked and we saw the humidity was high that day, and we knew we needed to adjust our temperatures. And we're not a multi-million-dollar like factory or anything. We made a real change in our process by leveraging software. So you can leverage both. You can if you're an electrical engineer, software isn't that hard. And if you're a software person or a developer, even front end, JavaScript, don't be intimidated. And you have to dive in. It's super rewarding, super fun. I'm going to show you how. This was like we made this Node.js app, and as we're like programming these boards, it's not live, so I can't mouse over, but like I can click and see what components are failing. So if I had like 20 failures in a day, I could be like, hey, everyone just stop, go home for the day. Let's figure out what's going on before we keep going, versus blindly, putting it on paper. We can actually do some analysis and see if there are any trends in our manufacturing. So there's never been a better time to prototype your product. I really believe this. And it's, don't let a fear of electronics stop you. 5 volts won't kill you. And most of it is not that hard. And I would even say it's more affordable or accessible than 3 years ago, right? So 3D printers, I know there was like a MakerBot out 5 years ago, but it wasn't, like I said, Barnes & Noble. You walk into Home Depot, Dremel has their own 3D printer. It's very much commercial now. It's very much available. Arduinos, I know Arduinos were out, but they weren't that popular. They weren't $5 on Amazon Prime. Raspberry Pis, a $35 Linux computer with, I think, 8 cores on the Raspberry Pi 3. Like a fully functioning computer. You wouldn't want to lose it, but if you did, you wouldn't be so upset. And I really think there's a distinct possibility that if we tried this 5 years ago, we would have failed. Because now we're able to solve problems in the physical world with code. This is a very broad definition, and I wouldn't even say it's like 100% accurate, but it helps demonstrate a point, which I think about strictly electrical engineering. You think about RF, radio stuff, EMI, analog design, circuit design, and you look all the way on the other end and you're thinking like front-end dev, architecture, data structures, computer theory, even just like programming. There's this kind of sweet spot in between that you would typically call an embedded engineer or a computer engineer or embedded developer. And you're talking about like low-level microcontrollers, FPGAs, which are kind of like you're programming a circuit on a chip. And it's not that hard to go one way back down. It's not hard to go the other way either, but if you had an extreme end and you really don't want to touch it, I highly suggest you do. And I always say that like a software developer who can like blink a light is dangerous, and dangerous in like a good way. Like I remember showing off a product that was like a super tight tolerance GPS card, and we had a bigwig in checking out the board and everything. We're like, yeah, it'll resolve down to this nit, it's this fast, and it's so efficient. And then the GPS light turned on to lock. He's like, oh, it lights when it'll light up when it locks on. And you're just like, didn't you hear anything I said? And the idea is that, and for me too, the first time you flash the LED, it's so satisfying. And it's like, I don't know if it's like some primal like lizard brain thing where you see fire, or you created fire, or I don't know, but there's something so fun about doing stuff in the physical world. And I think even a developer who is aware of it can speak all of a sudden now on a new level with a hardware designer. And Adafruit, I'm absolutely in love with what they're doing in New York. I was talking about my PCB manufacturer thing. It's nothing compared to what they're doing. Lamore is as good of a business person as she is an engineer, and she's like a badass engineer. And it's because if you go to the site, and if you have a weekend off, or if you have some time off coming up and you want to play with this stuff, there's this amazing thing where you have two great options to me. One is to buy a product and then see the things you can do with it, or browse the wiki, see the things you can do, and then buy the product on Adafruit. And so if you buy like a big 7-segment LED display and you want to make something for your garage or your kid's derby cars, anything, fix some, you hate your sprinkler system and you want to just fix this one thing, I guarantee it's on here. They sell anything and everything, and it's all well documented. And things have changed. I mean, this is in the beginning, I started talking about a 1.79 megahertz computer, and here's a computer for 50 cents. And that's 50 cents when I checked on DigiKey. This is not like the lowest price. If I bought it at 10,000, it might be less than a quarter, right? And it's a fully fledged computer that can start talking to sensors. One of the offerings that we have that I really love is a thing called Windows 10 IoT Core. So is anyone like a .NET developer or Visual Studio? Yeah, so they took Visual Studio. To me is one of the best IDEs. I mean, it's the only IDE I've ever really delved into, and it was kind of hard going that way because I was so low level and so down in the bare metal code when I was doing embedded C that I would never use an IDE. But the more I use it with IntelliSense and everything, I've I've always enjoyed it. I've always enjoyed how versatile it is in terms of debugging. I've always enjoyed, code completion. You don't even know open the documentation to see what a function does or what you need to pass to it. So Windows 10 IoT Core is an offering that runs on some common, pretty cheap devices, and Raspberry Pi is like the most common one. It also runs on the Minnow board, and I think there's a Dragon board was the other one. But if you were to start on a Raspberry Pi, basically you have a complete development solution right out of the box. So Windows 10 IoT Core is kind of a stripped-down version of Windows 10 that can run our Universal Windows Platform applications. And you can just download Visual Studio, install Windows 10 IoT Core on a Raspberry Pi, and start developing for it immediately. You hit the play button on you're still developing on your computer. You hit play, it goes right to the IP, and you target the device. And so over the network. So, it's just sitting there on the wireless network, your laptop's on the network, and you're developing for this thing that can now, because it's a Raspberry Pi, start speaking to sensors. So that's where it becomes really powerful. I'm setting a breakpoint on code that's actually speaking very low level. And if you think about that, it's kind of mind-blowing. If you talk about, it's not the same as the chart we had before, but if you're on the far end here, and you're saying .NET, the concept of color, capital C color, like a function that can parse strings and has presets, preset colors, and is thinking like 24-bit color space and alphas and things like that. It's so far in this end, and then now you can change an RGB LED, and you're pushing voltage. I couldn't think of two farther apart concepts. The highest level and the lowest level. And this will connect that for you, which means that if you are only comfortable in object-oriented, high-level space, you can start playing with the lowest level stuff immediately. You can do remote management of these devices through our portal, or our Azure offering. So if you had a Raspberry Pi as part of your product, you can start pushing down firmware updates. You can start receiving data back to see what's wrong with a certain device. You can turn them off. You can lock them out, provision them into groups. So you can try an A/B thing where you push the firmware here, and then you're waiting for the other one to see how it goes on this test bed, and then you can bring it over. So there's a lot of interesting things you can do just by virtue of the fact that it's a cheap device connected to a very complex system. And support devices are cheap. A Raspberry Pi 2, I think it's like $30. I think a 3 is 35, and I don't know if you can run this on the Zero. I haven't tried it. I don't think you can, but Zero is $5 if you ever want to play with that. And this is actually me developing an application. This is a real use case for something I needed for this company. And what I wanted to reveal here for people who have used Visual Studio is you still have full access to every component that Visual Studio has to offer. So you can create a complete UI by dragging and dropping and coding up your whole interface like you would code a Windows app. And it still is a Windows app. It's a UWP app, but it gets deployed to this Raspberry Pi device. And now all of a sudden you can make something like a kiosk or something with an interface, and you can test locally and then deploy remotely. And this is the basis for a lot of IoT, and I'm sure most talks cover this, but you have this Raspberry Pi and it has HDMI out, and that's great. And it has USB, and that's also great because now you can start hooking up peripherals. Then you also have Bluetooth and wireless built in. And to me, the interesting part, this alphabet soup down there, GPIO is general purpose input output. Basically means you can read a voltage as being high or low, or put out a voltage being high or low, even 0 or 5 volts, or whatever your system voltage is, which means now you can start interacting with buttons. You can start, putting out, you can start turning on LEDs and clicking relays and things like that. I2C or I2C, SPI and UART, those are communications buses. So it's a way to speak to smarter devices. And PWM, which makes a digital pin act like an analog pin, so you can start fading LEDs and start putting out power, voltage in different ways. So what's interesting to me now is this overlap, right? Now you have a device that can ferry data from sensors, and man, there are a lot of sensors, and start putting it out to your software. You can wirelessly upload it to the cloud. You can do local processing and then send the results. But the idea here is this is kind of like a bridge between the real world and your coding world. And this is just like a short list of sensors. And I really should break out any one of these we can talk about. I could spend the next 20 minutes speaking about. We can talk about all these ideas. Like if you think about this stuff in your process, if you have even something like your mailing envelopes and you need to dispense the correct amount of glue for your boxes, like you can build that in a weekend with Adafruit, and there are enough tutorials there that'll do it for you. And these are all the kinds of things you can interact with. From medical, you talk about ECG and EEG, brain, heart, muscle readings, accelerometers. If you had a product that moved and you wanted to analyze how well it was doing it, gyroscope, RFID tags is something I used recently. Same thing in your badges. It's just what you realize is that you can create the equivalent at home for very cheap, and it's not any less valuable than the commercial product, which probably costs hundreds of thousands, right? For instance, I wanted, just as a fun project, to have an RFID reader for my employees. Now they're coming and going. They have a key to my house. They're coming in and out, and I want to know how much they're working. And, I was paying them by the board, but maybe I want to pay them by the hour. I gave them these RFID tags. This little device there on the right was, I think it was $4 on Amazon. Most of those electronic shops are now Prime shops. So we wanted a way to dispense parts, because now we have 100,000 parts. We have reels and reels and reels of parts. And then also have kind of like a time card without having them manually enter. So they walk in the house, they just badge the Raspberry Pi, that little RFID thing, and I know how long they were there. And then when they log out, it automatically generates a PayPal statement worked. And then I know how long they were there and how much I got to pay them. Part dispensing and tracking, as they take these parts out, it's keeping count on my database on my cloud. So even if I had multiple stations, it's still pulling from a remote database, and I can know when I have to reorder more parts, right? And it dispenses only what's needed. And I talked about 3D printing. You're able now to create the tools you need to start making your business run more efficiently, right? So here was a way to dispense parts, and the equivalent feeder would be, I don't know, I think it's like a few grand. Well, for the old ones like the Samsungs, I think it's like 500 to 1,000 per feeder. But now I have one that I can 3D print for pennies of plastic, right? So things have changed and quite a bit. When I first started, I was coding assembly for a Motorola microcontroller, and it was archaic. And that was 8 years ago. It was not that long ago. And you must have seen it. Even how many have heard of an Arduino or played with an Arduino here? Yeah, I mean, it's no one. I feel like very few would have raised their hand not that long ago. And the devices, as they get cheaper and as they're open source and you're contributing back and you're kind of receiving the benefits of the fact that their design is open, and now Arduinos are $5. Most of the clones are $5. And you're not doing anything wrong by buying a clone in that case. It's supposed to be enjoyed. It's supposed to solve problems. So I'm going to touch briefly on some of the concepts that I can't delve too deep here, but I'm going to put up the slides, and anyone who wants to email me and ask questions about them, that'd be fine. But I'm basically here to tell you that if you want to go ahead and try, you really should try. It's not going to cost you a lot. If you don't like it, that's fine. But if you're a developer and you want to get your feet wet, you can go right ahead. And so some of this stuff, it's kind of anecdotal evidence I've picked up over years of doing this professionally. So you've probably heard of a data sheet, right? And if you've ever downloaded a data sheet and you've opened it, you're probably way, way, way overwhelmed. So libraries are great. If you buy an Arduino and there's something, let's say you had an idea for a product that was like a new kind of breathalyzer or needs to analyze gas in the room or something, it may not have a library for that. So their libraries are great for that, but if they exist, maybe they don't do what you want. And if they don't exist, you kind of have to write your own, right? So how do you interface with a component that doesn't have a library? And it's the big bad data sheet, and I kind of tilted this to make it look even worse. But it's actually not that scary. So this was a data sheet for that chip I showed, that ATtiny 13 before. All the information you need is highlighted in that orange bit. And I promise that's all the information you need. The rest are let's see, I think I annotated these, basically, 13 through 94, the pages that are not highlighted, those are like more details for the pieces. If you want to delve deeper, they're there. But you know everything you need to know usually in the first dozen pages. This is some serial programming information that's handled entirely by your programming tool, some clock and power characteristics you would care about if you were maybe like designing the battery for it and you wanted to make sure that it wasn't consuming too much power. More characteristics, even more characteristics, instruction sets, ordering info, package info, revision history, table of contents. So it's a lot of stuff, and it's not fluff, but if you're designing, you only care about a very, very small part of it. If you open it up, I'd imagine people scrolling through it and being like, this isn't for me, but it still might be for you. And so the first priority would be like, what do I need to know? Do I need to know the voltage of the chip, or what kind of clock to put in it, or whatever it is, or what kind of, what kind of commands can it take? So you make that decision before you open the data sheet, and then you look for what you want in a bite-sized piece, and then you're done. And all that information is relevant to somebody, but like a sliver of that is actually important to a designer. For instance, here's a page with the charts for the supply voltage on the left, and the one on the left looks, kind of crazy, and it, like I said, it's important to somebody. But for us, all I care about is, hey, what regulator do I use, a 5-volt one or a 3.3-volt one, and what are the implications of that? This is giving more information than you need. Here's what we actually care about on the right. So it's the information needs to be there for somebody, but not for us. And you should maintain an active curiosity when you open these things, because there's a lot to take away from it, but you shouldn't be discouraged if you don't understand something, because if I opened it, I could probably consume about maybe a quarter of it being a professional EE. And it's kind of a skill, so you should practice if you're interested in that. So I was talking about the Raspberry Pi before, and I was talking about the kind of alphabet soup on the bottom. And the interesting part about the device are these things called peripherals. So if you have a single board computer or microcontroller, pins can be configured for different functions. And this is just a Raspberry Pi, and what you see is there are some things that in like a purple color there that talk about SPI, and maybe the I2C is one of them. Can't really see from here. But you see GPIO, UART, which is like a COM port or serial port. So like these pins on this device can act in many different ways. And you typically call that peripheral. So now, you have a device you want to interact with. Almost all of the time, Raspberry Pi can. So if there's something you cared about, you wanted to use, and you found this oddball component that no one has used before for your product, you can interact with it, and it's not that tough. So GPIO is kind of like, how much time do I have? Okay. GPIO is general purpose input output, and it's usually the most basic function of a pin. So you can turn it to an input, and you can determine if the voltage present on the pin is high or low, meaning it crossed some threshold, 0 volts, 5 volts, 0 volts, 3.3 volts, whatever it is. So now you can start reading buttons, right? And output, you can do the same. You can set it to a high or low, and you can output voltage or output 0 volts. You don't really output it, but it's going to show as 0 volts, right? So what can you do with that? Now all of a sudden your input can check if a switch or button is closed to perform an action on the internet, or an external interrupt from another device, and now you can start networking this with a second Raspberry Pi and start exchanging data. Output, you can light an LED, control motors, activate relays. There's so much you can do with that. And here's an example. The syntax highlighting got a little messed up, but these colors would actually match the default color scheme, syntax highlighting in Visual Studio. So this is actually code from Visual Studio, and I'm running this, and I can drop a breakpoint on it. And it's crazy enough, if you hit that breakpoint and you're reading it, you can actually read the voltage as a property of your debugging. And like I said, it's like the highest level construct I could think of, but you're pushing low level stuff. And this is kind of the side effect of it. So if you imagine those 3 lines at the top, that's just kind of setting up. It's saying, hey, I want this pin to be an output. And then the 2 commands above the LEDs is the resultant action, right? So now I could flash an LED with C#. An analog to digital converter you may have heard of. So it's a numerical representation of the voltage present on a pin. So now you can start reading things like a potentiometer, a knob, like a volume knob, and things like that. So Raspberry Pi doesn't have an ADC, but Arduinos do, and a lot of the smart devices do. And just talking about, 99% of my job has been using passive components in the most common configurations, right? Because when you pick up a board and you look at it and you're like, holy smokes, there's no way I could ever understand this. If you break it down into small pieces, you're just going to see the same pattern over and over and over, especially in digital electronics, right? One of the ways you can start playing is there's a thing called Falstad Circuit Simulator. I highly recommend understanding voltage and current is kind of a tough concept to wrap your head around. And I've heard it explained a bunch of different ways where it's like, oh, it's like ping pong balls and a pipe or water. I hear a water analogy a lot for pressures, current, and things like that. The one thing I always wanted was something that shows electrons moving, that shows me which way the current's going. And you can actually see on this little RLC circuit, you can see those little yellow dots moving up and down, and that's which way current's flowing. And it was so amazing to finally visualize this in like my 30s, like be like, oh, okay. So this is like a little Java applet that runs in, I think somebody ported it to HTML5, but you can go in and start playing and start making circuits and see how they do. And you could see, if you see them move really fast, then you probably would have shorted the battery or whatever it is. But you can play with them in this little playground and actually see how they operate. And it's really interesting for analog electronics. Like you can make the equivalent of an AM radio with a few components, but it's fun to try. And if you don't have an oscilloscope and you don't have a multimeter, you don't have a whole test bench, you can still attach these points on the bottom to see how the voltage is doing. So you have like a virtual circuit and also a virtual test bench. And I just think that's so cool. So I had to cut a few slides for time. But most of out of all the equations I've learned over the years, I use Ohm's law pretty often, almost every day, and that's one of the simplest equations you can use. So a resistor is commonly used in a current limiting capacity. So you're talking about having a resistor in line, say with an LED, so it doesn't burn out. A pull up or pull down. Whoops, these pictures are gone. A voltage divider, provider voltage for components. Okay. I'm gonna cut this off for Q&A. What I'd love to do is I'm gonna put the slide deck online. I'll message everyone in the meetup, and I think there's a good amount of information left still that just goes over common components that you're gonna see every day. You're gonna see in all your products, and what they're most commonly used for. Because I'm gonna guess more often than not the things that I put in here, I'm covering 99% of how they're used. That's it. So, yeah, it's supposed to fit in a half hour probably. Does anyone have any questions?
Yeah. What's a common mistake you see beginners make?
Not trying. not even getting started. I see a lot of people who are. I mean, you can even go so far as. There's actually a great meetup tomorrow at the Reactor. We have a space in Grand Central, and I think they're covering JavaScript robotics. So there's Johnny 5, and it's a JavaScript robotics and IoT platform. Oops, sorry. I forgot this mirrors. Let me just exit there. There we go. So this is something for JavaScript developers. Oh. Oh yeah, it's actually Johnny 5. Yeah, I actually think there's an Easter egg. I think this is Jen. I can see her she's in there. But it's I think there are a lot of people who are scared of getting shocked or blowing a component or like setting their house on fire and stuff. But it's just not that way anymore. If you short something, most things have short circuit protection, and then like your voltage will go to 0 and the thing will stop working. And if it's USB, you'll hear doo-doo, and then you unplug it and then doo-doo, and it's back, and you're like, okay, no harm done, right? I would say I would highly recommend, like I said, if you have like a week off around holidays or something, I would just go to the site and start browsing around. I think it's under Learn, but it's essentially a live updated wiki. And sometimes I go on here and I'm just like, I'll order stuff and keep it in the box until I have like that first free weekend to like open up and play with it. And there are lots of things on here I've never played with. I mean, this thing's so cool. I would love one of these. But like I said, solving problems in your business or your startup, you might not even need like a proper engineer. You should just try it. I would highly recommend you try it. If you're hands-on, even if you're not a developer, and you're just here and you're trying to get your product to market, you want to just play, you should play. There's no doubt about it. But yeah, that's really it. Hey.
What language would you use if you wanted to be able to do things before you get frustrated and give up?
I think the Arduino. So Arduino is C-like. It's not quite C, but a lot of the low-level stuff is handled by the libraries that come with the Arduino IDE. So if you're comfortable in Visual Studio, I say Windows 10 IoT Core. But if you're learning to code, I would say get any Arduino compatible, and then to start writing to a pin or start putting out voltage is 2 or 3 lines. I mean, it's 1 line once you set up the pin. But within the IDE, I'm fairly certain. Do I even have it on here? I don't think I have it on this machine. Within the IDE, there's an examples drop down, and in the examples, there are a bunch of things where it's like turn on an LED, speak serial over a COM port. There's a list of things you can do in that, built in the IDE. You don't download anything, and when you open it up, it'll open the sketch. You modify it, save it as your own, and but it always gives you a nice foundation to start playing. Yep.
Curious about one thing. If you if a device wants to talk to another device, Raspberry Pi talking to another, I shouldn't have to go through the cloud and.
Oh no, yeah, right.
What's the ways? Through Bluetooth, through what Wi-Fi, what was it?
You don't even have if you want to do it wirelessly, you can do it Bluetooth, and you can do it Wi-Fi in a local network. You just do a raw socket to another IP address. But if you want to speak locally, you can just use what's called a UART, and a lot of people know it as like the COM port on the old computer, but it's basically serial. It has a baud rate, and you can basically connect the RX 2 wires, and now you can start speaking, sending messages back and forth between 2 devices. And almost every microcontroller really has a UART in it, a serial port, except for like the very, very, very low level ones. But yeah.
Sorry to cut off.
No, it's okay. I knew that would happen.
Yeah, but let's give a round of applause to Andy. Thank you.
Thanks.
Thank you so much.